Let's continue to learn Chapter 1, Matrices and System of Equations. Now we learn Section 4, Elementary Matrices. First, remember about equivalent systems. So far, we have learned two systems of equations involving the same variables are said to be equivalent if they have the same solution set. So we have two linear systems. They are equivalent because they have the same solution set. So AX equals B can be reduced to an equivalent echelon form by n-1 steps of row operations, and they are equivalent systems. So that's why we need this concept. We try to transform general linear system to the form which are easier to solve, such as triangular form, row echelon form. And we know that for linear system, when we solve it, we can use three types of row operations. And we can represent each row operation as a matrix after we learn in this lecture. And we do a sequence of row operations is equivalent to matrix multiplication. So after this lecture, you will know that for a sequence of row operations, it is equivalent to do a sequence of matrix multiplication. So in order to explain this, we need the concept of elementary matrices. So elementary row operations can be accomplished by multiplying A on the left by a corresponding non-singular matrix. To obtain an equivalent row echelon form, we can apply a sequence of non-singular matrices E1, E2 till Ek to both sides of AX equals B. And we get Ux equals C, where U equals Ek times E2 times E1 times A. So we pre-multiply a sequence of non-singular matrices E1, E2 till Ek, such that U equals this one, this multiplication. And similarly, C, this right-hand side vector also equals, we pre-multiply a sequence of non-singular matrices E1, E2 till Ek, such that C equals this multiplication. We have three types of row operations, and this lead to three types of elementary matrices. So type 1, an elementary matrix obtained by interchanging two rows of identity matrix. You will get an elementary matrix of type 1. And type 2, an elementary matrix obtained by multiplying a row of identity matrix by a non-zero constant. This is an elementary matrix of type 2. And corresponding to the row operation 3, row operation 3 means you multiply a scalar times one row, then add to another row. So this corresponds to an elementary matrix obtained from identity matrix by adding a multiple of one row to another. We can simply say that from identity matrix, if we do only one elementary row operation, we will obtain an elementary matrix. So from identity matrix to just one time of elementary row operation, we will get the corresponding elementary matrix. For example, here E1, you can see that this matrix obtained by we interchange the first row and the second row of identity matrix. We only do this one row operation. So this is a type 1 elementary matrix. And how about this one, E2? So for E2, you can see that we use the scalar 3 times the third row. So only do this one elementary row operation. So we get this elementary matrix. Okay, and how about E3? From the identity matrix, we use the scalar 3 times the third row and then add to the first row. So we get this elementary matrix. So this is a type 3 elementary matrix. Elementary matrices from the matrix A, if you pre-multiplying by EI, then this matrix multiplication, in fact, perform the same row operation of EI on A. And if you use A times EI, so EI is post multiplying by A, okay? Then this perform the same column operation of EI on A. We have this theorem. So if E is an elementary matrix, then E is non-singular first, and the inverse of E is an elementary matrix of the same type. So we know that from the identity matrix, you do only one row operation, then you will get an elementary matrix. And we know this elementary matrix is a non-singular. We will show in this theorem first. And also, its inverse is the same type elementary matrix. How to prove this? Okay. For E of type 1, it is obvious that E times E equals I. Remember, for the type 1 elementary matrix, it changed the order of two rows. If you change the order again, you will get the identity matrix. So, of course, E times E equals I. So, the inverse matrix is E itself. Of course, they are the same type elementary matrix. Okay, now we see type 2. For E of type 2 with one row multiplied by alpha, it can be transformed back to identity matrix by multiplying the same row by 1 over alpha. Therefore, the inverse of E exists and is also a type 2 operation, just using different multipliers. One is alpha, the other is 1 over alpha. Okay. And for E of type 3 with ith row multiplied by alpha and added to the jth row, it can be transformed back by subtracting alpha times the ith row from the jth row. So the inverse matrix of type 3 elementary matrix is still a type 3 elementary matrix. The multiplier, one is alpha, the other is minus alpha, subtracting alpha. Okay, we can see from the matrix like this. So Eij. Eij means we interchange the ith row and the jth row of this identity matrix. And its inverse, Eij inverse, just equals Eij itself. So if you interchange these two rows again, you will get the identity matrix. And for the second type elementary matrix, EIC, this means for the ith row, we use the scalar C, non-zero scalar C times this row. And it's easy to say that its inverse matrix just equals EI 1 over C. So the scalar now becomes 1 over C. If you use 1 over C times the ith row, then it becomes the identity matrix, right? Okay, now we see type 3 elementary matrix. So here we use Eij alpha to represent that this is type 3 elementary matrix, which is obtained from identity matrix using alpha times the ith row, then add to the jth row. Okay, so in order to transform this back to identity matrix, then we need its inverse matrix like this, right? Eij minus alpha. So if you use minus alpha times the ith row and then add to the jth row, you just eliminate this one, this alpha to be 0. So it becomes the identity matrix again.